Welcome to this explainer. Today we're diving into something that absolutely fascinates me. The sheer scale and, frankly, the wild ingenuity of human engineering. Think about it. From machines that can literally move entire buildings to engines pumping out enough juice to sustain whole towns, centuries of just relentless problem solving have given us mechanical systems so advanced they honestly seem kind of impossible. We've pushed the boundaries of physics, material science, and, let's be real, sheer willpower to build the modern world.
Okay, let's dive right into this. 100,000. 100,000, that is the horsepower generated by just a single diesel engine. To put that into perspective, your average car sitting in the driveway, it has about 200 horsepower. So we're talking about a scale of mechanical power here that is just truly staggering. Keep that massive number in the back of your mind, because we're going to see exactly what kind of machine needs that much raw strength a little later on.
So to understand how we got here, we'll be looking at four main frontiers today: shaping the solid Earth, conquering the high seas, powering modern human industry, and finally, reaching beyond our planet.
All right, starting things off with Section 1, shaping the solid Earth. Basically, how we first had to move mountains. Now, to build modern civilizations, humanity first had to engineer massive solutions to literally conquer the rock and dirt right beneath our feet. For the longest time, if a mountain was in our way, we just blasted it with explosives, right? But as our need for precision and safety grew, we couldn't just keep blowing things up. So we engineered enormous machines to literally eat their way through mountains. Modern tunnel boring machines are basically these giant mechanical worms, some longer than an entire football field. And what's absolutely incredible here isn't just their sheer size, but their dual function. As the front of the machine slowly grinds through dense, solid rock, the back of the machine is simultaneously building the concrete tunnel walls right behind it. It's literally an all-in-one moving underground factory.
Now, what's really interesting about this slide is the unbelievable contrast in how we move all that earth. On one hand, you've got bucket wheel excavators. These things use gigantic rotating wheels to continuously carve away entire landscapes, moving thousands of tons of earth every single hour. It's pure brute force. But on the flip side, we have hydraulic excavators. Instead of that continuous grinding force, these rely on incredibly exact fluid pressure. This tech lets these machines lift enormous heavy loads, sure, but they can also perform tasks so delicate and precise that a highly skilled operator could actually use one to pick up an egg without cracking the shell. It's a crazy spectrum.
So once we've reshaped the Earth, well, we have to cross it. And suspension bridges are pretty much the ultimate answer to spanning massive gaps, some stretching for several kilometers in length. The real engineering magic here, it's all about weight distribution and tension. By using these absolutely enormous steel cables, the structures efficiently distribute the immense heavy load of thousands of vehicles crossing them every single day. But here's the kicker: they aren't rigid. Actually, scratch that. They're brilliantly engineered to be flexible. They safely sway and adapt to withstand high winds, extreme temperature changes, and even earthquakes.
Moving right along to Section 2, conquering the high seas, shifting from solid ground to mastering the raw power of the ocean. The ocean is, quite frankly, an incredibly hostile environment, yet we've somehow built giants to tame it. Take giant offshore oil platforms, for example. These are among the largest movable structures ever created by humans. They're designed to stand totally firm, drilling thousands of meters beneath the seabed, all while taking a beating from powerful storms and massive, crushing ocean waves. And then back at the coastline, we have giant container cranes. These are kind of the unsung heroes of global trade. They pluck containers weighing tens of tons right off ships and place them onto trucks and trains with this absolute, millimeter-perfect precision. They're the workhorses keeping the entire global economy moving quickly and safely.
But wait, how do you actually move those literal mountains of cargo across the water? Well, remember that 100,000 horsepower figure I threw at you at the very beginning? This is the Wärtsilä RT-Flex 96C. It is a 2,000-ton diesel engine standing several stories tall. It's practically a building itself. This absolute behemoth is one of the largest, most powerful engines ever built, and it's precisely what's required to push those massive container ships, which are essentially floating cities, across the vast oceans.
Now, this brilliantly illustrates how our problem-solving has evolved when it comes to getting those massive ships up and over land. We've developed two distinct mechanical methods for elevation changes. The traditional method, like the Panama Canal locks, uses giant mechanical gates and millions of liters of water to slowly step ships up, a process of filling and draining successive chambers. It's a classic for a reason. But step 2 here, the Three Gorges ship lift, takes a totally different approach. It's essentially a giant vertical elevator that lifts the entire ship
Water and all, straight up in a single water-filled chamber. It's a real game changer that saves immense amounts of both time and water.
All right, on to Section 3, Powering Modern Human Industry, How We Harness Energy and Mass Manufacturing.
Now, before we look at the modern titans of industry, we need to take a quick historical breather. Long before computers, electronics, or even steam power, we had the mechanical clock. This was a true historical marvel. Using only precisely designed gears, springs, and escapements, early engineers were able to measure time accurately. And that tiny, delicate precision engineering? That basically became the foundation for everything else. It shaped global navigation, it advanced early astronomy, and it set the ultimate standard for the complex mechanical engineering that powers literally all the massive behemoths we're looking at today. Let's move to and see how this builds into modern industry, because this precision scales up massively. Think about heavy-duty truck engines. They operate at lower RPMs with super reinforced internal parts designed for pure durability, capable of traveling well over 1 million kilometers. That's no joke. Then, consider robotic car factories. We've basically scaled up the precision of a watch to thousands of massive robotic arms, welding, painting, and assembling 24/7 in this perfectly synchronized mechanical choreography. And to power the whole shebang, wind turbines. Standing over 250 meters tall, which is taller than a lot of skyscrapers, by the way, they're out there converting the simple movement of air into electricity for thousands of homes.
And hey, speaking of power, we absolutely cannot ignore hydroelectricity. Hidden deep inside massive dams are turbine runners that are quite literally larger than multi-story houses. The sheer force of millions of gallons of flowing water spins these gigantic metal wheels, converting all that immense kinetic energy into enough electricity to power entire metropolitan cities. It is just a breathtaking transfer of natural raw power right into human industry.
Which brings us to our fourth and final section, Reaching Beyond Our Planet, Pushing the Limits of Speed and Space.
Now, to get out there, you need incredible acceleration. And there's a super fascinating engineering overlap here between military aviation and amusement park thrills. So, on an aircraft carrier, the runway is incredibly short, right? To get a fighter jet from zero to takeoff speed in seconds, engineers use massive steam or, increasingly, electromagnetic catapults. And the crazy thing is, we experience this exact same technology on modern roller coasters. They don't use those slow clickety-clack chain lifts much anymore. They use the exact same underlying electromagnetic launch principles to accelerate heavy passenger trains to highway speeds in just 2 or 3 seconds. Same exact physics, just applied to vastly different human experiences. The crucial point is that to truly push our limits, we have to beat 2 massive persistent forces, friction and gravity. Maglev trains accomplish the first by literally floating above their tracks on magnetic fields. No wheels touching the rails means almost zero friction, which equals extremely high speeds and a perfectly smooth ride. And to beat gravity? Well, we engineered the Space Shuttle main engines. These are some of the most efficient rocket engines ever built, operating at extreme, mind-bending temperatures and pressures. It took decades of advanced material science to make that happen, so we could push a spacecraft right out of the atmosphere. Now, once we do break out of the atmosphere, we hit speeds that are honestly almost impossible to comprehend. 28,000, that is the speed, in kilometers per hour, at which humanity's largest outpost is orbiting the Earth right this second. I'm talking, of course, about the International Space Station. Traveling at that insane speed of 28,000 kilometers per hour, it is undeniably one of our greatest achievements. It connects thousands of complex systems just to provide astronaut life support, electricity, oxygen, temperature control in the dead, unforgiving vacuum of space. And then, even further out, we have the James Webb Space Telescope. Because it was way too large to fit in a rocket, it had to be folded up. Once it got to space, it executed this sequence of hundreds of perfectly coordinated mechanical movements to unfold itself. It was one of the most complex, high-stakes deployments ever attempted, and it worked flawlessly. It's literally letting us see the oldest galaxies in the universe right now. So, looking at all this, it's pretty easy to see the truth in this quote. Mechanical engineering surrounds us every day, often hidden behind machines we rarely think about. From the massive engines powering ships across our oceans, to the turbines lighting up our cities, to telescopes peering into the edge of time itself. These inventions are absolute testaments to human ingenuity. They prove our relentless ability to solve extraordinary challenges through science, creativity, and just absolute precision. Which leaves us with one final, very exciting thought to wrap up.
As technology and material science continue to evolve at lightning speed, the machines of tomorrow are going to accomplish things that we currently categorize as science fiction. So I'll leave you with this question to chew on. What impossible machine is being built right now? Because you know the next great engineering masterpiece is already under construction somewhere in the world. Keep your eyes open and keep learning. Thanks so much for joining me for this explainer, and I'll catch you next time.